Jerry, thank you. As rather than distinguished, I thought it was an extinguished scientist. In any case, I did have the great pleasure of working with Jerry on the ORAP panel. He was by far the best chair that we ever had, and they're probably still regretting the fact that he stepped down. In any case, I will do my best to take a look at what it is we learned from the soil spill, because I think in large part there are a huge number of questions that remain and will remain for a long time unanswered about it. I guess in one sense I was silly enough to accept the invitation of Jerry, and then later on I sobered up when I realized that I needed to interrogate a couple of hundred scientists to try to figure out what was going on. In any case, these are some of the people, just to, not to try to cast any blame, but to let you know that I really did. Hogarth is the dean and the guy who's done most of the work on fisheries about the spill. Robert Hine, Hollander is organic geochemist. Paul did microbiology and molecular biology on the spill. Peebles is a fishery biologist. Nancy Rabelais is a very famous person who did work in the dead zone in the Gulf of Mexico. Weisberg has testified repeatedly in Congress about this and what we could have done better. Wanenkoff is a famous scientist from AOML, who is a satellite oceanographer, Bern physical chemist. Kendra Daly, a very well-known food chain biologist, Short physicist. Van Fleet, organic geochemist. This guy's an engineer. Lemke's an engineer, and Simoniello's a biologist. So these are all people that I spent hours with trying to, and you'll be the judge about whether or not I really understood what was going on out there. So this basically encapsulates pretty much every academic facet of this. I always throw these guys on because this is the couple of Florence, my favorite ocean plankton, and probably many of you know the White Cliffs of Dover are made out of these guys. And when I was going to school, the school teacher would have a piece of chalk with billions and billions of little coccolithophorids in it. The significance of this is if it hadn't been for these guys, you and I wouldn't be here, because there'd be about 270 times as much CO2. The temperature on Earth would be so hot that we would have no water. All the water would be water vapor, and so there would be no life. So these are the guys that made it possible for us to be here in Long Beach tonight. In any case, just a few of the images, of course, that background on this incredible disaster in the Deepwater Horizon. Probably you've seen a lot of these things. It's amazing to realize they were dealing with 5,000 feet of pipe. And of course, as all of you know, the blowout preventer did not in fact work when it was called upon to. Obviously, when this huge mass of oil got to shore and into the wetlands, it's not a pretty sight. It's going to be there probably for a lot of years. These are also disturbing, and as we'll see later, the data on the survival of many of the larger organisms is pretty pathetic, as is the technologies that are used to try to prevent the oil from getting into the wetlands. And in fact, most of the techniques that were used in terms of this are obviously pretty crude, and they were developed very long ago, which gets to Jerry's point about are we any better off now in terms of dealing with an oil spill than we were a decade or two ago? And the answer is probably no. Some more incredible images from Louisiana, and some of the thousands of people were employed to try to clean up the beaches, which it turns out is a small fraction. The oil that got on the beaches is a small fraction of what was released out there. Okay. And of course, the skimmers, they spent millions on skimmers, and again, less than 3% of the oil was gathered up by the skimmers. This is a photo from space. This is Chuan-Min Hu's work, again, looking down at the Mississippi Delta here, there, and obviously the plume of oil stretching off toward the east. Now, as Jerry mentioned, this was in fact a really big spill. The biggest the biggest of any spills that's ever happened in the oceans. Not the biggest spill of oil ever that's happened. That was in California, okay? And that was on land. Nonetheless, in the ocean, in 1979, Isotope was a major spill too. So the Gulf of Mexico has had the two biggest spills by far. They dwarf any other marine spills. This is actually an aerial view of Isotope, which was on the Mexican continental shelf in 1979. And in fact, at that point, Governor Graham in the state of Florida was very concerned about whether or not the oil from that spill would get to Florida. And so they sent some people out, Ted Van Vliet and William Sackett, to actually take a look at the tar balls that were floating at the surface of the ocean. And they analyzed them and to try to determine whether or not, or they fingerprint them basically chemically to try to figure out whether or not the tar balls were from Isotope. And the answer was no. The surprising thing was, as you got offshore, you can see that inshore in western Florida, there was hardly anything there in terms of tar balls. And as you got into the open Gulf where there's beautiful clear waters, there's many, many more tar balls. Why? And where did they come from? And it turns out they figured out that they were the washings of the walls of tankers. Super tankers would go offshore after disgorging their oil in ports, and they would take high pressure hot hoses and wash down the walls. And so that practice theoretically is over now, but that is what they found, and they sampled for several years, which was a surprising result. And again, what our focus for this evening is up here where the Macondo well went off. One of the things that probably many of you witnessed May 12th was when the first video from an ROV was released of the well. And the interesting thing was a bunch of scientists took a look at this, and I can remember vividly on NPR radio hearing the description and the interviewing of the three scientists in the United States who had taken a look at this video and had estimated what the flux of oil out was. And of course, at this time, they were contending that it was about 1,000 barrels a day. And it was very interesting. I can remember an engineer from Purdue University using a completely different technique than somebody at Berkeley, and they came up with between 50 and 70,000 barrels a day, not 1,000 barrels a day. And in the end, they got pretty close to the mark. But the interesting thing was, this is a mistake. It should be April 20th. The estimates kept getting higher and higher, and at the end, I think the average was around 62,000 barrels of oil a day over the 87-day period that the well was active. That's an incredible amount of oil. And the interesting thing is that estimate is only the oil. If you look at these estimates, be careful about how you handle it, because it doesn't include the gas. And if you include the gas, there's another 30,000 barrels equivalent that are coming out as ethane, propane, butane. Okay, that's a huge amount now. And obviously, if you start calculating, and you're going to hear from other people about the natural resource damage assessment, whether or not the people finally decide that you have to pay fines based on this and this is going to make a very big difference in terms of billions of dollars to BP. Here's a few facts that I've been able to glean that I think are important and relevant about this spill. 96 days total. I actually, in looking at it, I think it's more like 87, but the other scientists say 96, so okay. 5,000 feet of water. This thing was about 1,500 meters deep. We'll see some cross-sectional stuff in a little while, but the base of the well was 18,000 feet below the surface of the ocean. Okay. 3.4 miles of pipe, 62,000 barrels a day, and it dropped at the end. As Jerry indicated, this probably would have gone on for decades. I mean, if you can imagine some kind of a giant global Michelin tire pumped up to thousands and thousands of PSI, like 12,000 PSI, and then hit it with a pin, and off it goes. That's huge. That's what they did. Because that's the pressure in that well was 12,000 psi. 2 million gallons of Corexit was used, and this is about the same amount as the Mississippi River empties daily into the Gulf of Mexico in terms of fresh water. It's slightly larger than the Isotope spill, completely different in the sense that Isotope was a shallow, okay, about 200-foot depth. This was released into deep water. It's the first discharge that I'm aware of that's ever gone into the deep ocean. And that's a very different scenario in a physical chemical sense than it is in shallow water. Okay, if we take a look at this environment, this is basically, obviously, the Gulf of Mexico, and with the major topographic features, the Campeche, the Carbonate Banks, the West Florida Shelf, the shelf off Texas and Louisiana, and superimposed on this, I put the loop current system. This is the major physical feature that determines where oil goes, okay? So this is an advective feature that is a precursor to the Gulf Stream. The flux of water through here is about 30 spheredrups. Spheredrup is 1 million cubic meters a second. So it's 30 spheredrups here. It's about 30 spheredrups out of the Straits of Florida. By the time it gets to Cape Hatteras, it's about 90 spheredrups. Just to give you a feeling for that, the Mississippi is by far the biggest discharge into the Gulf of Mexico. I think it's the 4th largest freshwater discharge in the world. This current right here is 1,500 times, carries 1,500 times as much water as the Mississippi River. Okay? It's gigantic. As importantly, this is not it's not fixed in space like I have. It's a very inaccurate picture. This oscillates a lot. Sometimes it comes in through the Yucatan Channel, it turns a hard right and goes out. In the case that when the oil spill took place, this thing had intruded up into the northern Gulf. So it's in like this, comes around and out. But it also spins off eddies, and in fact, it did spin off in mid-May a major eddy, warm core eddy, which, as we'll see shortly, had a lot to do with where the oil went and where it didn't go. And in fact, if people want to, they're going to be marching into the deeper Gulf of Mexico because that's where the big oil deposits are. They aren't even at the big oil here, we're at the edge of this system right here. Okay, up in here, the big oil is down in here, in the really deep Gulf. And so they're going to go down there. And the loop current's still going to be there. And what happens to the oil, the first order thing that happens to it is primarily going to be determined by this huge advective force that's coming in there. Okay. So let's see if we can take a look at this. The Weisberg and the physicists, the satellite oceanographers, took a look at this. So what you can see is in early May, when the spill had been going for about 3 weeks, the loop was coming in like this and then coming around like this. So basically it was sucking water down off this giant platform and then out. And in fact, it did it long enough so that the satellite oceanographers actually, although I haven't seen this reported in the papers, oil did in fact get to the north coast of Cuba. It was there, it was detected. Then the eddy broke off basically in, excuse me, in mid-June. And what that did was, in combination with the changing of the winds, it actually stopped. It stopped sucking the oil down toward the Keys and this coral reef system that's down here. And so it really saved the whole west coast of Florida from major damage. If we continued with this situation over here with westerly winds that blew anomalously for about a 1 week period, we would have gotten oil on the west coast of Florida, which is amazing. This, just to give you a feeling about how important this is, it took 1.5 months for the oil to get from the well site in the surface over to Pensacola. So that doesn't show real well here. The well is here, this is Mobile Bay, and Pensacola would be right in here. So it took 1.5 months to go from here to here on the surface. It only took 1 week once the wind shifted out of the west and you started sucking this, it took 1 week to go from here to there. And that's when the eddy broke off. So it was on its way, and the eddy broke off, and the wind shifted from west to east. So if you changed that around and you kept the westerly winds and you kept the loop together and not broken off an eddy, this whole shelf area would have gotten it in the Florida Keys. Anyway, that's of all the lessons you could possibly learn. I think that's the important one here. This shows what can happen. And this is somewhat like California in the sense that you get outwelling out here. You get basically deeper, colder water can be entrained onto the continental shelf and slope. So this is if we sliced Florida's over here and we sliced a chunk through all the way to the ocean. And this blue color means it's cold water coming up. And it gets trapped up here and then it's carried below the surface. So you can't see it in the satellite. But it moves very quickly, can move very quickly hundreds of miles on the continental shelf. And so this is a way to transport not just oil, red tide, larval fishes. It's a very important mechanism for the West Florida shelf. And it's happened historically. So let's take a look at just some sort of a context about the Gulf of Mexico as a fishery, and a little bit about the oil and gas industry in the Gulf of Mexico. The fisheries are fairly substantial. The commercial landings here are second only to the Pacific coast of the United States. Okay, so the entire Gulf has commercial landings valued at about 690 million. The west coast of Florida, where I live, is 150 million out of that. This is what you're talking about here is the total mass of fish is a little over 1 billion pounds. Louisiana part of it is mostly shrimp. And there's obviously 4 ports that do an awful lot of business with fisheries. Now, that adds up to 1.68 million fish a year are taken in of various sorts, and we'll take a look at that in just a second. What's staggering actually is a recreational fishery, which is much, much bigger financially than the commercial fishery. 3.5 million residents fishing, 24 million trips. You can see the number of fish they've caught, and it's $6 billion a year, so it's about 10 times the value of the commercial fishery. And the species by weight are listed right here. You might know some of these, and I have an image later. The king mackerel, this is interesting. I ran into these guys. The Southern Kingfish Association is a group of people who like to go fish for king mackerel. And a king mackerel, I don't know if any of you have ever caught one, they are incredible fighters. They're very high speed, they probably go 40 knots. And when they hit a line, you know you've got a fight. In any case, these people, this group, have about 200 tournaments a year. 200 to go after kingfish. Just on boats, motors, and lines, they spend 600 million. Okay, that's their contribution. So this is a big industry. I've been to a couple of these tournaments. It's staggering. See people walking around in matched vests and outfits. They have their own boats, dual motors, in some cases triple Mercuries that are $10,000 a pop. It's hard to believe. It's like its own culture. And it's all the way from North Carolina through Texas. And here's in terms of here's the king mackerel. That's a nice one, but that's not the biggest. And the rest of the top landings that we get in the Gulf, and of course something like the red snapper's not bad eating at all. A little bit about the continental shelves. The continental shelves here are in the Gulf of Mexico are extensive. In fact, the West Florida shelf alone accounts for 1 out of every 5 square miles of continental shelf in the continental United States. That's how big that is. It's huge. Obviously, the Campeche banks in Mexico are really big. The Mississippi River Delta is huge. This is a system right here. And there's a major, not just a major load of fresh water that's coming in there, but also sediments. This is a view of that system from space, and this thing has intruded rapidly into the Gulf. And thanks to a huge drainage system, this is about 40% of North America that drains into fresh water draining into the Mississippi River system. And it's caused some troubles that we'll see later in terms of creation of a dead zone in the Gulf of Mexico. It's also rapidly disappearing. This is a place where it's sinking fairly rapidly, so you're losing a lot of marshes, and a lot of sediment is going down into the deep Gulf of Mexico. We talked a little bit about this earlier. This is the discharge of the major rivers in the world. Amazon obviously way up at the top, and then the Mississippi is right here in fourth place with a little over 10,000 cubic meters a second. Okay, comparing that to 30 spare drips, 30 million per second in the loop current. Still, it's a very large freshwater discharge, and you do in fact see these big plumes of fresh water that come out from the Mississippi and go into the Gulf. And in fact, sometimes it's so substantial, you can trace those. They get caught up in the loop current, the edge of the loop current, and they're carried all the way around to North Carolina. You can follow the low salinity water, whatever that is, over 1,000 miles to North Carolina. The Gulf, I couldn't get away with about talking about the Gulf without talking about hurricanes. And in 2004, we live right here in St. Petersburg. We had 4 hurricanes come by. Charlie and Francis are shown here, but we also had Gene and then Ivan that tore up through the Panhandle. This was fortunately an autonomous measuring system that was offshore, because most of us are not silly enough to be offshore when a hurricane comes. And what you can see is this is a little over about 30 meters deep, that when Charlie hit, and Charlie was down here, this instrument was all the way up here, you can see that it actually, all of this colder water in the bottom just got completely mixed up in less than a day. It just turned the whole shelf over. And then the same thing happened here with Francis. We took the whole water column and homogenized it, so it was like a giant 8-liter. And this is the first time that I'd ever seen anything like this. Now, you might wonder, what does this have to do with gas and oil? And as it turns out, a lot. Because major hurricanes have gone right through. Each of these green dots is a place where oil or gas is being extracted in the Gulf of Mexico. Most of you know Katrina, in fact, was a major disaster, and that came through in 2005. And you can take a look at this. This is the impact of these hurricanes on the oil and gas industry. There are reports that Katrina actually severely damaged a major, very heavy crude storage facility that was dumped into the deep Gulf. It was really dense. That's just hearsay. I don't really know that for sure. But maybe someday they'll find out where that oil is. It's undoubtedly on the bottom if it's as dense as the people said it was. But anyway, this is a threat, represents a threat to the oil and gas industry in the Gulf of Mexico. The thing we talked about earlier in terms of being worried about the Gulf, the coral reef systems in the lower part of Florida are the only coral reefs in the whole continental United States. So, and they're already under duress. There's no sewage processing requirements in the state of Florida for the Keys, and so basically there's this huge danger bubbling up from below that they already are on the edge of things, and then you've got ocean acidification that's taking place that also is challenging the corals. So they already are in trouble. So if you add a little oil to the mix, that might be the end of the line for the Keys. Geologically, we can take a look now and go down and say, well, hey, why was this place such a great place for oil? Okay, why did the Gulf end up being a major repository for oil? And in the Jurassic, This was an area, a giant basin that was repeatedly flooded with seawater, and it was evaporated. It was a very dry, arid period. It was probably flooded dozens and dozens of times, and it evaporated kilometers of salt. And then you had these carbonate banks grown in shallow, warm seas. And that was followed by basically a very active volcanic period where a lot of carbon dioxide was pumped into the atmosphere. And very productive upper ocean, the plankton settled into the bottom waters, and since it was so sluggish, it basically chewed up all of the oxygen and created these black shales. Okay, so then this went on for millions of years. So basically, this was the organic precursor that got transformed into the oil. Okay. The final part of it was orogeny in the western part of the United States that raised the Rocky Mountains. The debris from that came down partially through the Mississippi River. It covered over this whole mass. And what happened was then that these giant salt deposits were basically metamorphosed into salt diapirs. And so here we go. This is a shot in Australia, but this is basically, if you can imagine, something that's a million times larger, that's got seawater in it. It's evaporating because there's a huge solar flux on it. And in fact, you're looking down at the Gulf of Mexico, you see the giant 6B escarpment that's just seaward of the Mississippi Delta. That's all salt. This is a giant chunk of salt, and I mean really giant. It's migrating very slowly. It's being metamorphosed and it's migrating into the deep Gulf. The significance of that is as follows. The salt domes are basically the metamorphosed salt are beautiful traps for gas and oil. It's impervious to gas and oil. So when the gas, basically the oil and gas that are produced from these organic rich deposits run into this, they get trapped. They're overlain in many cases by the clay-rich deposits that came down when the mountains were eroded. And so you've got these salt diapirs. And this is what they drilled in Texas when they first started drilling for oil, basically. But in deep water, it turns out there's a lot more of these babies. And you can see seismic reflection data. This is a giant salt diapir. It's probably a mile or two in dimensions. You can see the strata that are distorted as this thing is moving up to the seafloor. And there's hundreds of these things all over the Gulf, and that's what they're drilling. Okay. The challenge technically before had been that the oil companies, as I understand it, weren't able to look through the salt and find out where the oil and gas was. So if you had salt up in here, they couldn't discern, they weren't able to discern what was below her. And they finally have gotten mathematically adept enough, apparently, in their signal processing technologies are good enough now that they can actually figure out, even with the salt overburden, they can look through it like you could look at a tiny embryo or whatever and figure out exactly where it is. So that's the way that they discovered that the deep Gulf is this huge repository for oil. This just gives a little short history. 1947, the first oil rig was put in place that was out of sight of land. Okay, that's a fair bit ago. They're drilling in 6,000 feet of water now, but they'll be drilling, I think, fairly shortly in 10,000 feet of water, because that's where these giant oil deposits are. Okay, so what do I mean by giant oil? Okay, if you look at the estimates people have made for the oil in the deep Gulf, okay, so 6,000 to 10,000 feet, it's 44 billion barrels energy equivalents. Okay, so let's compare that to Anwar. Let's compare that to Alaska, okay, which they're drilling. Okay, that's 4. The estimates for the deep Gulf of Mexico, just the deep, not where the deep water horizon was, just the deep beyond this, 11 times bigger than all of Alaska. So it's one of the 3 giant, it's a mega province. So Iran, Saudi Arabia, the deep Gulf. So if we need to get oil, this is where we're going to get it. because we're not going to get much more on land. We can get the gas, not the oil. In any case, you can already see if you take a look, that one map I showed you, this is just a salt and pepper. There's thousands of these platforms, 3,000 platforms here in this area, 490 active platforms that are working right now in relatively shallow water, because this is all continental shelf and slope areas. It's not really deep, okay?
How many wellheads does a platform serve?
I have the impression now that they might be able to do 7, maybe as many as 10. You might know more about that than I do. I'm not an oil specialist, so that's a great question. My impression is that they can drill in many different directions, and whether or not that's synonymous with being able to service all of those things too, I'm not sure. Given the cost of the rigs that are drilling in deep water, you're talking about an investment in the rigs alone of $1 billion. Just to put one rig out that would do 10,000 foot drilling. So that's a huge investment. So this is just the last in terms of like the slide about this. Are we running out of oil? No. The deeper we go, the more oil we find, and you can basically see what happens. Inshore here, these are the daily production rates down in 1,000 to 4,000 barrels a day. This well, this accident, this disaster, we already know it was about 62,000 barrels a day. So when you get into really deep water out here, you're probably talking about 100,000 barrels of oil a day. Okay, that's a lot. It's a huge amount of oil. And again, these are major investments to put one of these things in. So they do it. They do it carefully. Okay, a little bit about the lessons learned. Somebody made a comment about the government, and my impression is that in fact there needs to be a lot more concern about the safety on these production wells and drilling platforms. And you could probably say, well, that's a classic no-brainer. I think the culture, and Jerry referred to this earlier, here was let's get the oil out, and that was the focus. It's not about checking the dashboard and making sure, are these readings okay? And was anybody looking when they knew the gas was coming up, was actually going onto the platform? Because there is a mechanism for shunning the gas off so that the gas doesn't come onto the platform. So that's what happened. The gas got onto that platform, came up that pipe very, very rapidly, and instead of getting shunted aside, if somebody had been watching, they could have seen that and shunted it off, and instead it got onto the rig. Probably a spark in one of the generators ignited the thing, so that's what happened. But anyway, my contention is there needs to be a lot more regard for safety. I think the other thing is that if you can possibly get to the oil before it gets to the shoreline, it would be a big help, because getting it out of an environment like this is impossible. You basically have to wait for bacterial degradation to do it in, okay? Because it's not only that, in this kind of an environment, if you're out in the open ocean, the evaporation rates are going to be really high. If you're in here and adsorbed plant materials and everything, the evaporation rates are going to be way down. I did want to, oh wait, I don't want to do that quite yet. I also wanted to say something about the way this was handled by the federal agencies. And I'll admit ahead of time to having some considerable prejudice, not against federal agencies, but for my academic colleagues. I listened to a program in NPR that was interviewing Vernon Asper. Vernon Asper is a graduate of MIT, Woods Hole program. I went to sea with Vernon Asper for a month. And Vernon Asper talked about how he was out in the middle of the Gulf of Mexico, and this is in May, and had discovered a plume of oil. And the first thing that happened was NOAA officials and the Coast Guard officials said that it was impossible, that this guy was crazy. Okay? I mean, if I hadn't known this guy, what would I know? But I knew Vernon Asper. Well, the stunning thing to me is it wasn't just Vernon Asper. Many of the people whose names you see on the slide I talked to you about before, who are really famous scientists, were also impugned by the same federal agencies. Ernst Peebles, Robert Weisberg, David Hollander, Samantha Joy from the University of Georgia. The list goes on and on. The astounding thing to me is that instead of hurling whatever it is you're hurling across the table, it would be better to say, look, I'd love to see your data and let's talk about it. Why do you think there's a plume? On what basis are you making that judgment? That didn't happen. And this happened repeatedly. And in fact, it's a violation. There's a thing that was published in 1988. You can look it up on the internet. It's called the 7 Cardinal Rules for the federal government. It's the 7 cardinal rules of how you react and act in an emergency and in a disaster. And that's one of them that's covered. And that isn't how you do it. Okay? So in any case, I thought it would be instructive for us to very briefly and quickly take a look at the 3 major controversies that involve the federal agencies, NOAA and the Coast Guard, and academic scientists. And the first one is basically, there's no submerged oil, okay? There aren't any plumes. This is the CEO, or former CEO, of BP, okay? This is the northern Gulf of Mexico. Here's the Deepwater Horizon. Here's some sampling sites where the University of South Florida and other people sampled. This you want to pay attention to. This is the DeSoto Canyon, which it turns out is going to play a big role in what happened to the oil. And this is a cross-section. If we could slice down from the north to the south, this shows the temperature in the upper part of the ocean is very hot, and you get down to this well and it's about 3 to 4 degrees centigrade. So it's very, very cold down there at 1,500 meters. This is just a picture of the Weatherbird, which is the small research vessel that this group of people went out to take a look at the cruise. It turns out both the Woods Hole scientist and the mathematical modelers from South Florida had made projections ahead of time about what would happen to the well, the oil that came out of the well in deep water. And it turns out that they predicted that it would go both to the northeast and to the southwest. And in fact, that's exactly where the plumes were found. The Woods Hole people found plumes on the, I can't remember the name of the ship, but they found a 22-mile-long plume in this direction, and the South Florida people found a major plume up here. Also, that's University of Georgia, University of Southern Mississippi, Florida State, on and on and on. This is a 28 kilohertz sonar. This is a rosette sampler going down through the water. This reflection is oil, okay? This is 400 meters, 400 meter depth horizon is right here. And this is probably about 30 to 40 meters thick plume of oil.
Peter,
Yeah, sorry.
give us a little bit back on a plume. Is that oil that's escaped, or that's bad, or is it evidence of something gone awry?
Yes, it is. You'd never see this in a normal ocean. I mean, you do get plumes of reflections, but the plumes and reflections you get are from, for instance, organisms that are populating the deep scattering layer. So you'd get a reflection from things like euphausiids, shrimp, migrating fishes, so on and so forth. They subsequently sampled, so they proved unequivocally that it's oil. This is initial evidence that something's very different about the deep ocean you'd never normally see. So basically over here, oil is pouring in at 62,000 barrels a day. This stuff is It's actually very complex because the oil mixes and is entrained with the deep water, and there's not just a plume at 400. There were plumes detected in several levels. So, in any case, hopefully that answered your question about plumes. This is a sampling system, so you've got a rosette on here with, say, probably 24 bottles. They send it down through the water column, and they basically can send the signal down. They can sample wherever they want. This is a picture of one of the filter pads. This is the filter that came back from filtering particles that are greater than about half a micrometer in diameter, so that's half a millionth of a meter in diameter. This is particulate material that was filtered from the water, and what you can't see here on this, because you need a more powerful microscope, is that this is populated largely with 50 to 60 micrometer droplets of oil. Okay, that's a lot of what's down there. They sampled the water and they analyzed the water using a gas chromatograph mass spectrometer, and basically found out that the particulates that they filtered from both 400 meters and 1,000 meters were anomalous in terms of their composition. They weren't plant material. They weren't normal carbon materials that you'd find in the ocean. And as we'll see a little bit later, they used a very fancy technique to take a look at exactly what this stuff was and where it came from. So anyway, each of these samples that they took from 400 meters and from 1,000 meters of particulates, they're hydrocarbons, and it didn't matter where they were in terms of how many nautical miles from the wellhead. They got the same patterns. These are very high concentrations of hydrocarbons, so many, many hundreds of times greater than what you'd normally find. So in any case, that's not so good. So anyway, there is oil beneath the surface, so this is just showing that they were wrong about that. So the next question is the oil on the seafloor, and is it toxic? Is the oil both in the water column and on that's been deposited in the sediment toxic? And so it turns out when they sampled, they took box cores from this region. This one is from 2,300 meters, so it's from considerably deeper than the well itself. But basically these little clusters that are fluorescing, it turned out are all oil particles. The thing is loaded with them. And in fact, all of the box cores they got had oil.
What's the size of those cores?
Those are probably, let's see, I'm not absolutely sure, but normally they would be about 1 foot on a side, roughly. Some of the mathematical modelers took a look at the oil, the size of the oil droplets and their densities, and then took a look at, tried to calculate what their distributions would be in this area of the DeSoto Canyon. And what you see is here that the number of particles, the number of particles basically is very, very large. It's up into thousands of particles per liter of water, so thousands of particles that are 50 to 60 micrometers in diameter per liter of water. Now, what's sort of sobering about this is that if in fact this canyon that's right here is an upwelling zone, which it is, right around the corner, this is probably the most productive carbonate bank. It's the middle grounds, it's called, fisheries on the West Florida Shelf. So if you get this, basically the hydrocarbons up onto the shelf and into shallow water, and it gets carried in here, then you're talking about potentially fairly substantial consequences. And I think we spoke a little bit earlier about how we were very lucky about how the winds and the loop current prevented that disaster from happening, but it's still, they went and sampled the water column to see whether or not there had been upwelling in the canyon, and indeed they did. They found that while they had seen this oil down in a couple hundred meters on their first cruise, on the second cruise, it had gotten up to 35 to 50 meters. So basically that cartoon I showed you where you saw cold water upwelling onto the shelf, that's exactly what happened here. And it brought the oil up onto the continental shelf. So the next thing that happened, the next very incredible interaction with BP people was that they said, well, you know, there's a lot of natural seeps in the Gulf of Mexico, so you're going to, it's probably not the BP oil. You know, the 62,000 barrels a day isn't enough to get a signal out there. So you've got to prove to us unequivocally that this is actually oil from that well. Okay, well, okay. So anyway, David Hollander thought that was a wonderful challenge, and he's a very good analytical chemist, and so they gathered samples of mousse from the surface of the ocean. They managed, thanks to the help from one of our congressional groups, to get a sample of the well oil itself. BP was not willing to give the oil until they got pressure put on it. And what he did was analyze this using compound-specific isotopic analyses. Now, I know that's your favorite technique at home, but this is incredibly powerful. So what happens is that you run it, you take a very small sample, you can take a couple of micrograms of a sample, you heat it up in a gas chromatograph, and basically it runs it through a very tortuous panel, and as it's running through, it separates up according to its molecular weight. So the light stuff, the gases that are really light, low molecular weight, just race through. Okay, it's like Indianapolis 500 zing, and they're out. The really heavy stuff is sort of like, you know, and they're staggering through. So by the end, you're getting this really heavy, goopy, awful stuff that's coming out. And what they can do is they can sort of chop off. They chop each of these things off as they come out, and they run it through a mass spectrometer. And they measure the carbon isotopes. So they measure the ratio of carbon-13 to carbon-12, which it turns out is diagnostic. So for each of these classes, they're actually taking a look at, and you can see over here what they call the del C13. So it's basically the degree to which either there's more heavier isotopes or lighter isotopes of carbon. It's incredibly powerful fingerprint, okay, about a lot of things. For this oil, it really is. So there you go. There's what they did for the oil from the well, okay, that they got. This is interesting, and just, I guess, another wonderful thing that you'll like to share with your kids. This oil, it turns out, is distinctive, incredibly distinctive from all the other oils that we know about. Its isotopic signature is easily discernible from every other oil we know about. So you can't mix it up. This is not Nigerian, it's not Venezuelan, it's not anybody else's but this one, okay? It fits right in here where there's a big gap. I mean, the people who have done this, and so, you know, you might in some cases run into oils that are down here and they look an awful lot like Wyoming oil. This is really distinctive. Okay, so then the next question is, how does the subsurface stuff or the surface oil compare to the BP? And this is again using the isotopic, compound-specific isotopic analysis, and that's incredible. And again, this is the comparison between the subsurface oil that they collected in the DeSoto Canyon, and the black is the Macondo. I asked David Hollander why he didn't have data here, and he said the samples were too small. We didn't have enough material to get the isotopic analyses. But nonetheless, you see there's enough of an overlap here to unequivocally link it. Now you might say, what's going on down here? And that's a very good question, because basically this stuff doesn't look like the mechanical oil at all, right? I mean, it's different. Okay, so what happened? It turns out what happened is the bacteria got presented with a wonderful dollop of food, and they just chopped the daylights out of this. So all of the light stuff, the ethane, propane, butane, it went in a flash. And in fact, that's how some of the scientists got into a fight, because one group was reporting, bacterial degradation of the oil, and the other group was saying, no, it wasn't. And so you can see how that happens. If you're out there and you're looking at low molecular weight stuff, well, it's disappeared. So it had to go, right? If you're looking at high molecular weight stuff, it's still there. The bacteria are going to have to work a lot longer and harder to get that. That's not good stuff. And some of it's probably been metabolized, and it's a whole lot nastier after it's been metabolized than it probably is when it first was let loose. Okay. In any case, that sort of takes care of the whether or not this is BP's oil. Okay, the compound-specific isotopic analysis shows unequivocally the stuff in the northern Gulf is theirs. The last point is it about the toxicity. And just quickly, John Paul, who's sort of a National Academy of Science level molecular biologist, went out and did some tests using just natural water samples that they had captured on the West Florida shelf and mixed it up. And what he did is he looked at both the responses of the bacteria, so the really tiny guys out there, and he looked at the dinoflagellates. And when he looked at the dinoflagellates, of course, our natural phytoplankton are out there. He looked at the suppression of their photosynthetic pathways. And it turns out they were suppressed. So these are the stations, PCB03 and DSH08 are the ones where he got suppression. And this is where the oil droplets were found. Okay, so basically, we can't say exactly what it was about the oil or what set of compounds that was toxic or inhibited. What we can say unequivocally is that there was some part of that mixture that was, in fact, deleterious to both phytoplankton and bacteria. Okay, and in any case, this just sort of summarizes everything. We are, in fact, getting sedimentary oils. We're getting upwelling onto the continental shelf, and the oils are moving through the canyon, and in fact, there's some good data that, in fact, it's toxic. After I had started, or actually after I left to come out here, I heard a report from a Penn State scientist who worked in the DeSoto Canyon area, who was taking a look at Lophelia, which is a scleractinian coral. So it's a hard coral. The Lophelias are found 1,000 meters roughly all over the world. They were first discovered off Norway. They took a look at these guys off the DeSoto Canyon, and I haven't read the report, but basically the report that I heard on NPR was that there was substantial damage to the scleractinian corals in the DeSoto Canyon. So there's an awful lot more work that has to be done before you make any hard judgments about it, but what you can say unequivocally is that at least in some places there has been substantive damage by the oil. I don't know, Jerry, do you want to take a short break, or I don't know what you normally do, or have people, I'm sorry I didn't say it, I'm happy to take questions if some of this is opaque or whatever. I've got some more stuff that relates to actually some of your materials that you introduced me with.
Why don't, let's take about 5 minutes for questions, then we'll take a short break. Anybody have any questions or observations? Yes, Larry and Zan. Or Zan and Larry.
Go ahead.
I had a question about subsidence. If you're pumping over the land does it sink? Or, you know, does it put back in? Or
Um,
what?
That's a good question. I don't think that basically there's any subsidence. You probably will have some adjustment of some, because it's unconsolidated sediment. So you probably would get some of the clays and or the silts moving slightly to, or adjusting. You might have a small fall, but this is not, geologically it's not a major, it's not like a turbidite flow or something like that. I don't think that would be the case.
Larry?
Has anybody looked for or found oil on the bottom?
Yes, they have.
Sediment. Here's the water is sediment. And that's got the same isotopic signatures and
Yes.
stuff for it.
Yes, it does.
Because that could be there a long, long time.
Yes.
Probably will be there a long, long time, whether it just got there or
Yeah,
whether it's been
exactly.
there forever.
That's a really good point. And in fact, one of the things, and that's probably, you're getting to something that I was always sort of perplexed about the media. Would always talk about Exxon Valdez. And they routinely compared the Exxon Valdez spill to this thing. Well, it's completely different. Exxon Valdez was in shallow water, this is in deep water. Exxon Valdez basically was a benthic, almost totally benthic associated, so bottom, cobbles, pebbles, whatever. And they used high pressure hoses, and they apparently destroyed the benthos to the extent that it's, and there's still problems up there. The herring have never come back. It's a classic case of it took 4 years. It was 4 years before the herring left, and all of the other areas in Alaska that didn't have anything to do with oil, the herring are still there. But the herring have never come back to that sound. The only thing that would be similar is when you get down into deep water where you've got very cold water on the sediment now in the Gulf. But even that's different because the sedimentary arena, this is all clays, very finely divided clays. What you had in Alaska, it was almost subaerial, was big cobbles and pebbles and everything else. And so you've got a completely different flora, completely different fauna. It's not really comparable. But the temperatures are so low in the bottom of the ocean, and I suspect that if you get a coating, number one, the degradation rates are going to be low because the respiration rates are low. Okay, that's number one. Number two, if you smother the bottom and you've got an anoxic system, then all of a sudden you create an anoxic system. So you completely switch over the bacteria, and the degradation rates, they probably don't have to tell you. They're completely different. Yeah, they go to pot. They don't go. You just don't degrade very much.
Bob?
You mentioned the bacteria took care of some of the lighter molecules, and the scientists were seeing different things. Then you said that heavier molecules were going to be metabolized. I didn't understand what you meant by that. And then you said that's going to be worse.
It is.
Could you elaborate on that?
Yeah, I'm sorry, I apologize, it probably was. Much of the lighter stuff was, all the evidence that I've seen metabolized very quickly. And in fact, probably at the surface of the ocean, that's probably not right, it probably was evaporated. So in Isotope, for instance, in the first week, 50% of the oil went out, okay, because it evaporated. Okay, but the question about the higher molecular weight stuff, some of it does get metabolized.
What does that mean?
What is that? Oh, I'm sorry. Oh, okay.
But you said
Okay.
the lighter stuff got taken care of like bacteria. What takes
Yes,
care of the
okay,
heavier?
the lighter stuff basically gets transformed to CO2 in water. Okay? So that's,
So the bacteria can't take credit for that.
yes, they do. Oh, absolutely they do. Bacteria do that, and they do it wonderfully fast. Okay? So they'll take a sugar or a carbohydrate or whatever, and you break it down. Oh, you basically take, plants put CO2 and water together, and they form a sugar and oxygen. And so you just think about those four little things. And what the bacteria do is they reverse that process. They use oxygen, and they rip the daylights out of that sugar or the carbohydrate, and off you go, and you get water and CO2. Okay? So it's just, the plants are pushing it one way, and the bacteria are running it the other. I don't know. So the bacteria also will attack and go after some of the bigger, say, multiple ringed materials. Benzene, well, benzene's not a multiple ring, but benzene, toluene, things like that. And it turns out that they probably don't reduce it all down to carbon dioxide and water, but you're left with, they knock off a few hydroxyl groups, or they alter it slightly. And in some cases, what you're left with is not very nice. It's called a metabolite, and the metabolites can be very, very toxic. Okay? The point is, we don't know what's going on in the soup.
So metabolites still are an oil compound.
You're right. Yes, absolutely. It's a slightly modified oil compound, so it would still have 28 carbons in it. But what happens is that they hang different groups, or they modify the groups that are the nitrogen compounds, or hydroxyls, or COOHs off, and they modify it, and it turns out it completely modifies its reactivity.
So I'm at a national meeting, and a federal government agency person says it's all been taken care of by the bacteria. There is no more oil. That's what I heard. So
Well, I would say that, I guess my question to them would be, how do you explain the results of all the people from universities that are independent academic people who went out on different ships at different times and didn't talk to one another and come up with diametrically opposed conclusions? They're really careful people. They're totally honest. They don't have an axe to grind. I wouldn't believe them. If I heard somebody say that, I'm sorry. They're done. Okay, no, I'm serious. There's no way. They're irresponsible, or they're incompetent scientists, or both.
Before we take a break, then I just want to reinforce, this is a very special place, the Gulf of Mexico. It's been referred to as the nation's gas station, the nation's fish market.
Yeah.
And over geologic time, it has been subsiding. So if you look at the relative rate of sea level, for example, off the Gulf compared to California, it's 4 or 5 times as great. Now, whether the removal of oil has accelerated that, I don't know, because while the amounts are large in one sense, they're not very
Well,
large.
yeah, that was a very interesting question that she asked, because and I've been thinking about it more, because like, for instance, when you look at the Mississippi fan, that extends for probably 600 miles under the ocean. So during the Pleistocene, you lowered sea level way down, and then all this stuff from the Rocky Mountains came rolling in, and it's hundreds of meters thick. And the pressures that are exerted from that are, of course, in many ways responsible for those salt diapirs coming up. And so you're talking about masses of material that dwarf the amount, the oil, these little specks of oil that we're dragging out. I mean, in one sense, it's huge what we're doing. In another sense, it's nothing. It's like comparing the Himalayas to a little nubbin.
So we've got something like 4,000 platforms.
Yeah.
And probably something like 40,000 wellheads, and maybe 35, but it's a large number. And it's interesting. Most of us think that the largest oil producers are in the Far East or the Middle East, and in fact, the U.S. is the largest consumer and producer of oil in the world. We forget that. We still have to import over half of what we use because we have such an insatiable appetite for oil. And as Pete said, we're progressively moving to deeper water because that's where the oil is. It's oil under very high pressure, so when you have one of these incidents, it's really tough. It's a tough, on the one hand, it's an amazing engineering marvel that we are able to do this.
Yeah, it is.
But we have probably not invested enough on what happens if something goes wrong. One of the things that we found out in this forum that we had with federal people and from the oil industry was that no one had ever contemplated that something like this could ever happen. It never occurred to them that this could happen. And we heard that from NOAA, from the Coast Guard, from the Minerals Management Service, and from the oil industry. And now one of the lessons is we have to think about the worst possible thing that could happen and prepare for it. Someone mentioned that the lack of a safety culture. A safety culture means that if you're on one of those rigs and you see something going wrong, and the way things were going wrong on this for weeks before this happened, just like we did on Alpha Piper in the North Sea for weeks, if you have a corporate safety culture, then you know that you can shut the operation down and that you will have the support of the people up the administrative chain. And it's called stopping the line. And this is when Toyota is one of the companies that has this great reputation that if anybody sees anything wrong, they can stop the line. Now, they've had a lot of recalls. They can argue about that. But it was very clear that there was not a culture of safety on Deepwater Horizon. Before we take a break, who knows why the name Macondo? We've heard the BP's blow up, we've heard Deepwater Horizon blow up. Anybody Macondo? When they lease these areas, they give them code names so that if I'm from BP and you're from Shell, I don't want you coming over. So, and often when they open up a new field, they might say, well, we're going to name these after drinks. You might have whiskey, etc. And Macondo is a town out of Naval, and so they had named these new finds after old towns. And then later, they of course give them different names after people have filed, they paid the fees, and now it belongs to BP and so on. But it's a fascinating thing, the way we go about all this. We were asked to bring people together because there was concern whether something like this could happen in California. We have these oil islands. One of them is probably no more than 100 or 200 meters from where we are right here. And then we have a small number of offshore rigs. First ocean well was here in California. And the short answer is it couldn't happen in California for two reasons. First of all of our wells are shallow wells, so they're not under very much pressure. The second thing is, though, California has this amazing audit of every well, and it's done by a third party. And now the federal government is looking at California, and they're looking at staffing levels that California has for its small number of wells, and what it would take for the federal government to have comparable audits of wells in the Gulf Coast of Mexico. So let's take a 10-minute break, no more, and then we're going to come back and wrap this up.
Okay, just quickly, I wanted to take a quick look at some of the marine mammals and what happened with in regards to the oil spill. What you can see here is that the turtles, basically 594 died. They collected 536, and of those, 28% they were able to release them. Okay, that's not terrific. So a lot of loggerheads died. The birds are really bad. They seem to sit around and take it until it's way too late. And so you basically had a 15% survival of the birds. The dolphins and whales were the worst. This 3% of the collected organisms made it. And that's pretty bad. And then the thing that we don't know about, and this is, I think I asked Jerry this earlier, somebody made a comment about the only thing you had to worry about were tuna and the whale sharks, and I disagree. This is an image of a dead sperm whale floating south of the Macondo rig. And what happens is, most often, large mammals, when they die, they sink to the bottom. You don't see them, okay? So they're deadfall. And in fact, you've got quite a bit of that out here. This is a little shot from the Santa Cruz Basin right there. That's a whale deadfall in the Santa Cruz. In any case, I think we've got a while to figure out what's going to happen with the whales. These, in terms of good news and bad news, these are the little coquinas. I don't know if many of you have been in the Gulf beaches. These are they're by the thousands and thousands. So if you watch the tide slosh in, you see these guys, and they're filtering like mad. They've got these little filters out, and they're filtering like mad, and then dig their way down, and they get below the sand level. Right after the oil spill in Pensacola area, they were completely wiped out. There wasn't one of these left that anybody could find, and within a month and a half, they're all, as far as I can tell, they're all back. So this is the only population I know that did real well. So the little coquinas are doing just fine. Thank you. The populations that I think are probably at risk that we won't know about for a while, the whale sharks. Okay, they're giant organisms. These things probably average 27 feet long. I mean, it's probably like a small school bus. Okay, they filter algae. They have a very fine filtering system. They not only feed through the filter, they breathe through the filter. So if you put oil droplets, 50 to 60 micrometers, and thousands of them per liter, these guys go through many hundreds of cubic meters of water a day. Okay, so it remains to be seen what's going to happen to the whale sharks. And it turns out this is right here is a particularly critical region. This is where they cluster. Okay, so the Macondo, you could hardly have or have picked a worse spot in the ocean than there to have an oil spill. Sperm whales, it turns out, and I was surprised that one of our scientists at the University of South Florida has a big acoustic array in the West Florida Shelf, and they can hear the sperm whales coming by. And it turns out that the northern Gulf is a critical area for the sperm whales. There's a big population in the northern Gulf of Mexico again. So this is, you saw the picture of the cryptic mortality, the dead whale floating off the Macondo rig. It's going to be a while before we know what's happened to the sperm whale population in the northern Gulf of Mexico. Finally, the bluefin tunas. They spawn in the spring and the summer. So when the skull went off, this is when they were spawning. This is one of two areas in the world. I'll repeat it. There are two areas in the world where this fish spawns. Mediterranean Sea, northern Gulf of Mexico. We may have some trouble here with the big guys. In fact, they've tagged some of these off Nova Scotia, and one of these had the good sense when they swam into the Gulf of Mexico during the oil spill, swam around the oil spill and went right out of the Gulf. I mean, okay? So maybe they're real smart. Who knows? The big problem here is, just a second. We already talked about this, basically the egg mortality and the herring population in the Exxon Valdez area. It took 4 years for it to appear, and they've never come back. The herrings never come back. Okay? So we're not going to know for a while, because the big problem here is, what is the oil going to do to the fish larvae? Okay? That's the fundamental question, not the giants, the larvae. And so here you are. This is a bluefin tuna larvae just after they're hatched. They're out there. They're in the midst of this oil patch, and they might survive, but they could also be impaired. And I don't know, probably most of you appreciate the fact that limping tunas don't last real long. Nothing that's impaired in the ocean lasts very long at all. You're eaten. It's an opportunistic world. It's worse than trying to sell Toyotas when you've got a bad deal, see. Anyway, not a pretty picture. And again, we don't know what's happened out here. And one of my major concerns is why do we not have money in the federal government to basically support the fundamental research necessary to understand what's happening with the population? We don't. Okay, so anyway, impaired organisms, and there could be a whole big bunch of them.
Well, does any other payment that BP is mostly going to make, does that go to support the research?
I think that's a good question. They're just starting to talk about that. So you'd hope that would be the case, but every day that we wait is a day that we've wasted.
But Peter, as I mentioned over dinner, BP has provided $500 million to ocean leadership and its competitive funding for academic scientists. It must go to academic scientists, and there are no restrictions other than it can't be for engineering or response. So there would be no reason it couldn't go to this.
Okay, that's interesting, Jerry, because none of the people that I interviewed were aware of that, and they are very up to date on where the money's coming from. So I have no doubt that you're right, but it apparently has not been widely distributed in terms of letting people know that there's going to be a competitive round of proposals that are going to whatever. We badly need it. That's the whole point.
The foundation is funding the research, the corporation is funding the liability. It's different piles of money.
Oh, I'm sure there's obviously you've got the NERDA fines and you've got other damages and everything else, and the question with regard to what the Gulf states are going to do with there's the estimates of between $5 and $21 billion that the Gulf states are going to get, and that's over and above what Jerry's talking about. And so that's a much bigger pile of money, and I would contend that some of it ought to go into an endowment that's used in perpetuity to support good research into what happens with the oil. I wanted to just mention about the one potential worry. We've talked a lot about big animals, mammals, turtles, so on and so forth. One of the things we haven't talked about is the fundamental or the base part of the food chain, and one of the organisms, this is a copepod, so this is one of the herbivores in the ocean that's incredibly important. It's not just important in the Gulf of Mexico, it's important all over the world. It turns out that these, at times, chelinoids, deposit their eggs in the sediments in the fall, in the winter, okay? And then they're supposed to hatch. They'll hatch the next spring. If in fact there's sedimentary oil that coats the eggs of these organisms, it'll change their ability to respond to the photoperiods. And the photoperiod is the thing that kicks in that tells the egg, okay, it's time to come out, okay? So this is an experiment that's going on right now that we don't know the results for, because we know they're eggs in the sediments. So the chelinoid copepods, that would be a really serious thing if you mess that up, because then that's really basically a fundamental building block for the food chain for the Gulf of Mexico. Now, we talked about the water column. We haven't talked about the benthic populations. In other words, the question about what happens to the oil that gets down on the bottom. And one of the things I wanted to mention is that many of the organisms there, like crabs, are completely dependent on what their incredible ability to sense trace amounts of chemicals. They have the most sensitive noses in the world, and actually we do too. If you were put up against the best chemical instrument in the world and that could measure hydrogen sulfide, I guarantee you'd win every time, unless you don't have a nose. Okay? You can detect far smaller concentrations of hydrogen sulfide than the best gas chromatograph in the world. Well, the crabs, the big crabs that feed on the deadfall that come into the ocean also have incredible olfactory sensing capability. And if we could have that video.
She just went to get a new player, Peter.
Okay. In any case, This has only been seen by like 5 people in the world. What happens is they took a submersible, they took a bag of dead fish down 500 meters and put it on the bottom. And you couldn't see anything. All you could see was the bottom, just sediment, for as far as you could see. Nothing is there. Within 20 minutes, the bag's covered with giant golden crabs just ripping those herring mullets out to pieces. So they followed it upstream, and they probably were tracing cadaverine or whatever the amino system is that's in the water, but they probably were detecting, like thousands of molecules. Something that the best chemists in the world would have a real hard time doing, okay? So here's the point. The point about that is hopefully we'll see the pictures. But people will go out into a water body, whether it's the Gulf of Mexico, Lake Tahoe, or wherever, and they're going to say, well, I can't detect whatever. Benzene, toluene, you name it. Pick your favorite poison. The point is, that doesn't really relevant. The point that's relevant is, what is the detection capability of the organisms in question, okay? Now, so I took a look at this. I went back to one of the greats of ichthyology, Ronald Barrett, and an engineer from Worcester Polytechnic. And they did some measurements on fishes, various fishes. And the common goldfish, okay, a goldfish, wait, this is incredible, can actually detect 20,000 times less methane than the best underwater mass spectrometer that the Germans, the Americans, or the Japanese could put together. Okay? A goldfish. And the goldfish isn't close to being the best. Okay. So when I say what's undetectable may still be a problem, that's a very serious issue. Okay? In any case, if we ever get this video played, I know you'll be impressed. Okay, that's not the only problem. Here's the golden crab. This is a big dude. This is the size of a reasonable dinner plate. A male and a female carry about 3/4 of a pound of meat. So the crab itself is a 2-pound crab or so. And they're very fast on their feet once they get up and running toward dead fish, or dead whales, or dead dolphins, whatever, you name it. They're there and they're prepared to eat it. But they're not alone. Basically, isopods, amphipods, hagfishes, all of these things have incredible olfactory sensing. So if you've got a lot of oil droplets in the sediment, if you've got clouds of oil down there, the potential is there to really make it impossible for them to feed and reproduce. Nothing serious. In any case, the other thing I think that's a real worry is, probably most of you know, this is common all over the world. There are a host of organisms that are part of the midwater communities that migrate every day in response to light levels, changing light levels. The ones in the Gulf of Mexico, during the day they're living down about 500, 800 meters, and at night they rise up into the upper 200 meters. In California, during the day, you're maybe 200 to 400, and at night, organisms out here would be at 50 meters, okay? It's a more productive upwelling system. It's a completely different, some of the organisms are the same. These are much more, they're waterier. They have a lot of water. Okay, less muscle. Now, if you look closely, you can see this is a fish, okay? Those blue eyes, and this is a lure, okay? And that's a mouth that's studded with teeth. And the midwater fishes are generally about 1/3 choppers, 1/3 body, and 1/3 tail. So they're completely, they're set up to do one thing: eat whatever it is that comes along. Some of them are so good that they can actually disjoint their jaw and stuff in something bigger than they are, which is pretty neat. Okay, so you get the lanternfishes, the bristlemoths, and this is a nice little guy. Take a look at that. They lie in wait when they're down there, and they're waiting to get and eat. Here's a little hatchetfish. This guy is incredible because these little things are light pipes, and it can adjust the light, the downwelling light, so that it becomes invisible. It does counter shading that would make a nuclear submariner proud. Okay. You cannot see this guy. It's unbelievable. Also turns out that these organisms all have a tremendous olfactory and optical sensing capability. Same thing for the larval octopods and also the larger ones. And then here's the anglerfishes, one of the anglerfishes, sorry. So you got to imagine this is in a completely black ocean. They can light this up using a cold light, luciferin luciferase reaction, and woe be unto whoever it is that stumbles in, because you're gone. You're toast, or hors d'oeuvres or whatever. Here's the fang tooth, and you can see it can actually unhinge the jaw, and so it can swallow something bigger than the mouth opening. It's quite a trick. Nonetheless, it does it routinely. In any case, I put these up because I think that the mid-water column organisms are the ones where you really have tremendous potential for disruption. Number one, their olfactory sensing capability is incredible. So some of the things that are going to be at low concentrations that we don't think matter could matter really a lot to them, because it could make it impossible for them to communicate, to even detect their prey. The gills, their gills could get coated. I mean, forget the not being able to use olfactory sensing, but if you coat their gills. And then the other thing is, if you've got a plume or a high concentration of a gas or oil, like you saw in that one image, it could be a barrier to the diel migrations and stop them completely. So it means that at night they couldn't come up and feed. Now, I'm just bringing up things for you to think about. It's not that this is happening, I'm just saying this is something people needed to study, because it is in fact a serious issue. These communities are found all over the world, and this is something that could be going on in the Gulf that we really need to worry about. Finally, there's some, to end up, I have just a couple more things, Jerry, besides I hope we can get the VHS tape going. Here's a fish kill in Louisiana. It has nothing to do with oil. It has everything to do with oxygen. So these are normally bottom-living fish who got in an anoxic environment and no oxygen, and they died. Now, we talked a little bit earlier about that formula, about CO2 and water going to sugars and oxygen, and this is where we get in trouble in the ocean. This is where we can get in trouble with oil going into the environment, okay? The dead zone in the Mississippi River is a classic example of this, and see the well, the Macondo well is right over here. This hypoxic area, or this area where there's no oxygen for much of the year, is to the west, which is incredibly fortunate, because if it had been to the east, we'd have ourselves a real mess. It's not that we don't right now, because this area is greater than the size of the state of Massachusetts. Okay? So it's an area that has zero oxygen in it, that is over 20,000 square kilometers. Okay, and that's right. Why is it? Because all the nutrients coming down the Mississippi River fuel this incredible production of algae. The algae settle to the bottom. So like in this incredibly productive period when you created all these organic rich shales that became oil, now you've got this going on here. And it might be okay if you really wanted to wait around long enough to get oil, but the people in Louisiana want shrimp and they want fish. And if you get low oxygen, you don't get any of either. So if you go through that area where you used to be able to fish and you try to crawl, there's nothing there. It's all dead. Now, okay, and here you're all looking at me like, what the heck does this have to do with the oil spill? This just shows that the nutrients, especially the nitrogen is the big one, are being fed through the Mississippi River system into the Gulf, and it's been expanding. And basically, what you basically have is if you put in more nutrients, you get more plankton, more carbon going to the bottom. So as the little beasties die, they settle out to the bottom. So you're taking the carbon down. You basically reverse that formula we talked about. So you're basically taking the oxygen, reacting it with the sugars using bacteria, and boom, off we go. we've got hypoxia, and that's not pretty. Okay, so what about the oil and the gas that's coming in now from that Macondo well? What happens when you put in basically all of that methane, huge amount of methane, and those, the ethane, propane, butane, on and on and on, that we know has disappeared? The bacteria processed it, right? So what happened? They ran that formula backwards, okay? So that means the oxygen went down, but it also means that the, somebody like this could be affected again, because he's going to be sensitive to having no oxygen. In fact, he wouldn't be living. If you take the oxygen to zero, you kiss the apifauna, the macrofauna goodbye, and all you'll have is bacteria. They're gone. There goes the possibility in the midwater columns. Again, if something like this, fish had to go through a zero oxygen layer, I can guarantee it won't happen. And the reason I know that is because if you go to the Cariaco Trench, which is one of the great repositories for hydrogen sulfide in the world, the upper part of the ocean has got oxygen in it. And there are fishes up there that live, just like in the normal ocean. And only one fish in the world is capable of going, that we know, into an anoxic area that's got hydrogen sulfide in it or no oxygen and surviving. Everybody else stays away. So if you get this in the middle part of the water column, one of those layers at 400 meters or at 1,000 meters, and I'm not saying it's happened, but if it does, we've got a problem. So there's some major chemical processes going on that could alter the Gulf. And just to give you a feeling for, this is a major alteration. This was a series of calculations done by a guy named Rick Weinenkoff, who's Mr. Ocean Acidification for NOAA. And basically what he did is calculate what would happen to the saturation for an unstable mineral that it turns out is a major part of the pteropods, little snails that are in the ocean, if you oxidized 40 micromoles of methane. So that's 40 millionths of a mole per liter of water. That's not a whole lot. And you might actually have come close to that. So what happens is the oxygen goes from about 100 and, well, whatever it is, 25 or 30 low here, and it drops down to about 60. So it's not anoxic, but it's below the level that the shrimp and the fish live in Louisiana. Okay? As importantly, or maybe more importantly, everywhere from 500 meters to the bottom of the Gulf of Mexico, you've completely changed the saturation state for the little houses that the snails live in. So instead of being stable, they dissolve. Okay? You've taken the ocean and completely tipped it over. So these are some of the things that I think, as somebody who's just a concerned citizen, you'd have to be worried about. Okay, so to end up, I have some big lessons that I think hopefully you certainly don't need to agree with them, and they're in no particular order. The first one is we're going to need a whole lot of years to understand what happened out there. Okay, and by that I mean my feeling is we're going to need at least 1 decade and possibly 2. Okay, for a lot of reasons. This is a major deal here, and my nephew is smart enough to understand I shouldn't have been surprised by this, but the public perception of this event was devastating to the state of Florida and to the state of Louisiana and to Mississippi and Alabama, and I'll explain why. I listened to a guy named D.T. Minnick, who's the head of the Tourist Development Council for Pinellas County. Pinellas County is the smallest county in the state of Florida. Just happens they have some beaches. The dollar flux associated with tourism in that county was $6 billion a year. Immediately after the oil spill, the canceled bookings were 30% of that value. They lost $1.8 billion in a week in bookings in Pinellas County. one county, the smallest county in the state of Florida. Okay. In Louisiana, I have watched and listened to and read about those poor fishermen that have perfectly good shrimp, oysters, and fish, and many, many people around the country refuse to eat it. They say if it's from the Gulf, it's unsafe. And so the perception is this is polluted stuff, and it's not. The oysters that got hit with the oil are gone. They're not around to eat. In any case, these are just two examples of how the public perception controls things. I mean, Pinellas County, Florida, the oil never got within 300 miles, okay? And yet, the people in England, Germany, every place else just stopped. So that was it. Politicians, they ought to stick to what they're doing, and they ought to stay out of science. There is a classic example, I will not name the politician, and maybe some of you read about it, the big berm project in Louisiana. And this idiot and his colleagues demanded that they build a berm out of silt and clay, okay? The United States Geological Survey went in and said, look, you can't do that. It's gonna go in about 2 days, and you'll spend millions building the berm up. They said they didn't care, and so there's pictures of these dozers working away. And sure enough, it went. And they had actually told them not only should you use sand, but they told them where the sand was, and they were ignored, and the berm project went forward. So anyway, that's enough of that. Exxon Valdez, we already talked about it. It's not equivalent to the Gulf of Mexico, and it's not a particularly good thing to use. The oyster and shrimp industry, certainly, I just put this in the poor people, I feel sorry for them. They got nailed. Federal, state, and local officials, I think Jerry probably already went over this, they were not well prepared for this disaster. And I talked to, I have a friend, Ernst Peebles, who is a very good friend with one of the people who was in NERDA. And this guy said that for 2 weeks after April 20th, he never got one phone call, one word, one email from his bosses in Washington, D.C. about what to do, about the oil spill. Not one. If it hadn't been Ernst Peebles, I would have had a hard time solving that, but that happened. The academic scientists, I was actually very proud of them. I thought they did an awfully good job of reporting as soon as they got something and putting it out, talking independently. They were willing to talk to one another and argue about what they found. I thought they were a breath of fresh air in this, what was a mess. We already talked about the seven cardinal rules, and I think the government ought to go back to 1988 publication and use it. There are seven cardinal rules, and it's time to start. Let's see. We need a way to respond quickly to these disasters, and we certainly don't have one. There's not only are the scientists, in many cases, know what to do, they don't have the instrumentation to do it. Not only that, they don't have the money to support going out to sea on the ships. So some of that money ought to be, fine money, ought to be set up, used to make it possible for competitive proposals to be funded to do that. Now this last one was amazing, and I have a personal story to tell about this. The BP and NOAA, and I don't know how many of you know this, tried to hire, and in some cases did hire, hotshot scientists, oceanographic scientists. Okay. I know one physicist who was hired. He was working on an underwater mass spectrometer, and I had been talking to him, and he had done some profiles of near the Macondo site quite by accident before the spill. And then BP found out about it, and they hired the guy. They hired him through his firm. He didn't really know what was happening. As a result, he couldn't talk to me. He couldn't tell me anything about what he was doing, where he was going, or what he was, I knew what he was measuring. And I actually called him up on his cell phone, because I have his cell phone. And he was closeted in some place in Louisiana, getting ready to go out on a ship, and he said, look, Pete, I'm sorry, I'm not at liberty to tell you. Okay? So his data was embargoed. He got thousands of data points. Well, okay, I guess if you feel like you're going to court, that's one way to operate. But if you're really trying to understand what we need to do to make, to understand the system, then I don't like this. But that's going on. It's gone on. And I think it ought to stop. I have nothing to say about it. Finally, an awful lot of the biological damage, and certainly have no way to know how much, is hidden from view. It's cryptic. That would involve the corals, so we already talked about the hard corals that were near the DeSoto Canyon, the diel migrators that are there, the olfactory sensing people, the benthos, and of course the larvae, not just the bluefin tuna, but the larvae of many other organisms that could be coated with and or influenced by the oil. In any case,
Wait, before she plays it, I'd like to offer 2 friendly amendments to your lesson.
of course, listen,
And people can
your amendments are always friendly,
People can
Jerry.
reject them. I would say that there should be something on there about the media. The media behave very irresponsibly. The
Okay.
NOAA Science Advisory Board, we had a meeting in the Gulf, and it was interesting that you talk about the public perception, but it was the guy that was the head of natural resources for the state of Mississippi. He said, you've characterized, this was now in August, you've characterized this as a disaster. He said it wasn't a disaster environmentally. Katrina was a disaster. This was a terrible problem, not a disaster. Now, whether it turns out to be a disaster, as you say, Peter, I don't think we know yet. But clearly,
Right.
a lot of people's lives and the economy took a terrible hit because of reporting. And we have an event at the Aquarium tomorrow. NOAA is having a press conference here, and it's about seafood, the Gulf, and whether you can eat seafood safely. So if you want to eat some seafood from the Gulf, we'll give you a free pass to the hospital if you get sick. No, you won't get sick. It's tomorrow morning. Yeah, my other amendment would be that I think we should keep in mind that the Macondo blowout was an event. It was an episode. It was a terrible episode that never should have happened, but it was an event, and I think we should be much more concerned about the chronic stresses on the ocean, like ocean acidification and the loss of 30% of the total phytoplankton biomass in the last 40 or 50 years, both of which are driven by the releases of carbon dioxide from burning fossil fuels. And if we're going to not have these kinds of events, then we have to reduce our reliance on fossil fuels.
Oh yeah, I agree, Jerry. I wasn't taking that next lead. I
Oh,
was
no,
going to
I-
focus on the
Right. I think those are very
issues
good
at
lessons.
hand,
Now, we're gonna, as they say on the 10 o'clock news, we're gonna roll the tape.
Okay, here we go.
Is it cute, or did you want me to rewind it from the beginning?
No, it's cute, ready to go, sorry.
Okay, great.
And John says if this lasts more than 20 minutes, he's here.
There's a bag of dead fish, and there's these golden crabs.
Four is on the track, on the bait, sorry, and chases away crab one.
You can see, there's one up here. These guys are having a little trouble controlling this baby. This is obviously not a Toyota submersible. But they're huge. These are big crabs. And by the end, I mean, you cannot see the bag. Okay?
There's an interaction which results in the crab falling off the bait's bag.
Okay, so this is at the Continental Slope. It's about 500 meters deep. And they dove down to this bag of dead fish. And it obviously drew a very appreciative crowd. That's enough. Thank you very much. Anyway, that gives you a feeling for the olfactory capability of the crabs.
So Peter, let's take just a few minutes for questions.
Sure.
Just asking both of you off the top of your head, it seems to be a big issue. You're talking about the media. And with science in general, the public generally has this perception of how science is presented through those media sources. Is there any way that you guys would suggest that scientists can come out and be more vocal about, this is really what's happening, because it seems like that doesn't come across as much in the media. Is there any way we could change that culture of the media just jumping on something and taking it either politically in a different direction or whatever bent they're trying to get to it?
Peter, what would you say?
Actually, it's interesting because in our area, I thought that the scientists were the St. Petersburg Times, which is the biggest newspaper in the state of Florida, did I thought a very good job of actually taking quotes from David Hollander and Ernst Peebles and Bill Hogarth, Bob Weisberg. Weisberg ended up testifying in Congress a couple of times. Senator Nelson came and has visited the laboratories. I mean, the spill was, the disaster was obviously bad in many ways, but it did highlight the importance of the scientists that were working, and they actually became rock stars. I mean, these people who normally are, hidden behind some computer terminal or with a series of equations that are opaque, there they were because they had to. They were thrust into it. You're still going to have trouble with people who want to grind a certain axe.
Right.
But,
it seems like that with a lot of incidents that we find that it seems to go in a certain direction. I mean,
Yeah.
you don't see them as much. I mean, this one was one where you actually saw a few, but
right.
it's almost like we need to get that out there. And I don't know
Mhm.
if this will be a future direction that we go. Is maybe the media will start being responsible, especially on the news media outlets, the 24-hour
Yeah, that's our.
news media.
I thought NPR. I didn't hear everything obviously, but the things that I heard on NPR I thought were really balanced. I thought they were done very well. I mean, you might not agree with their, but I don't get the impression that they have a slant that they're trying to do, and the people that they interviewed, I thought they did a very good job. And I suppose that Fox News would be a little different take on things.
Why don't you just call on people here?
In the media, we heard a lot of talk of the use of dispersants. Is that something, from your take, something that's useful in these deep oil blowouts, or are they pretty much useless?
Well, I don't think it was a good idea to use it. And the reason I don't think it was a good idea, I think we sort of went over this a little bit already. If the oil, you get the oil to the surface, then a lot of the low molecular weight stuff that can evaporate will. And that takes a burden off the deep ocean that we don't need. We already have enough in terms of stresses on oxygen systems, and I mean, that's sort of what it basically says is you really don't care about the ways that the midwater and the benthic webs function. If you get it to the surface, it's not that it's perfect or that it's not doing damage, but it's my feeling is it's a lot less likely to be doing damage. If it's at the surface, you can track it with a satellite, you can send ships after it, and you're going to evaporate probably 50% of it in very short order. So.
Do you think that dispersants were used to protect the ecosystem or to hide how much oil was spilled?
Well, I mean, sure, I am prejudiced that way. I think it was probably done to probably keep as much as you could in deep water. But I suspect that they probably didn't understand the physical chemistry that well, because it probably a whole lot would have ended up in deep water anyway. They probably influenced some of it, but not as much as they thought they would. Just because you get these emulsions that are formed in this, basically there's a mixture of very dense water forming and emulsifying with the oils that you don't get in shallow water. So they're trying to model that right now. So if you throw in the dispersants, I suppose who knows, we'll find out eventually if it's a 5% thing or a 50% kind of thing. I'd rather see the oil go to the surface for a lot of reasons.
But I from the media and everything, had the impression and knowing that you're going to emulsify a 10,000, 12,000 PSI stream of thing, it's going to turn into somewhere between mayonnaise and ice cream. I thought the dispersants were to keep oil off the shore. You know, they'd rather have mayonnaise deep than oil on the shore, because the wetlands were, and everything were so would be so heavily affected.
If you manage to get it on the bottom, then the damage that you're going to do was, you're talking about much longer periods of time to recover than you would if you put it in the wetlands. Because the bacterial degradation rates in the wetland are probably, I'm just taking a guess, probably 10 times what they are in the deep ocean. Yeah, or whatever. I mean, it's just huge. The other thing is, all of the epifauna, and probably a lot of the infauna are going to go. And then if you knock it over to an anoxic system, everybody's dead except the bacteria. So I mean, if that's what an emulsifier accomplishes, that's snatching defeat from the jaws of victory. So, yeah, I don't know. I'm sure that eventually a report will come out that will give us some insights into this, but I just assume they didn't use dispersants.
But, and I think part of it is we haven't really had good studies of dispersants and how they behave and what they do.
Right.
And the report that we've had is that now for the first time, the data were collected that will allow an analysis to be made to determine the efficacy of dispersants and any kinds of adverse impacts they've had. So I'm hoping that's the case. We'll take one more. Anybody have one more they would like to ask?
Yeah, John's going to ask, when are we going to go?
John. I think this has been a great introduction, Peter. We thank you very, very much.